Welcome everyone. In this video, I'll go over the ideal gas equation and give you 5 top tips to help you answer questions on this topic. Then, I'll go through an A-level chemistry exam question putting these techniques into action. Let's get started. Tip number 1, you have to know the ideal gas equation. PV is equal to nRT. It will probably not be given to you in the exam. This is certainly the case for OCR and AQA specifications, but check your specification. You will not need to derive the equation for A-level chemistry exams. Tip number 2, you have to be able to rearrange the equation. There are 5 rearrangements. Let's go through each one using PV is equal to nRT as a starting point. To make P the subject, divide both sides by V, giving P is equal to nRT over V. To make V the subject, divide both sides by P, giving V is equal to nRT over P. To make N the subject, divide both sides by RT to give N is equal to PV over RT. To make R the subject, divide both sides by NT to give R is equal to PV over NT. And to make T the subject, divide both sides by NR to give T is equal to PV over NR. If you really struggle with rearranging algebraic equations, this is a really good place to start. There are 5 terms, so slightly more challenging than the other equations involving amounts and, well, you need to know them anyway. Tip number 3, know what the variables represent. This will make it so much easier for you to recognise where to use the ideal gas equation. P represents pressure, V represents volume, N is amount of substance, R is the ideal gas constant, which will be given in the question or on a datasheet, and T is temperature. Tip number 4, know which units to use for each variable. Pressure in pascals, volume in meters cubed, and amount of substance in moles. Depending on the data that you are given, the ideal gas constant is 8.31 or 8.314, and this has units of joules per Kelvin per mole. And finally, temperature is measured in Kelvin. Tip number 5, you have to know how to convert between units. Let's get started with pressure. There are 1000 pascals in a kilopascal. To convert kilopascals to pascal, multiply by 1000. An easy way to do this on your calculator is to use the exponential function. Multiplying by 1000 is the same as times 10 to the power of 3. To convert from pascals to kilopascals, divide by 1000. This is the same as times 10 to the minus 3. There are 1000 kilopascals in a megapascal. This gives the conversion factors shown here. And if you need to convert between megapascals and pascals in one step, we can use times 10 to the 6 and times 10 to the minus 6. Next, let's look at volume. There are 1000 centimeters cubed in a decimeter cubed and 1000 decimeters cubed in a meter cubed. The diagram shown here for converting units of volume is similar to the previous diagram for converting units of pressure. Temperature will often be quoted in units of degrees Celsius in exams. This scale is based on the physical properties of water. Under standard conditions, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. We can relate to water freezing as a cold temperature and water boiling as a hot temperature. Dividing the difference between these temperatures into 100 equal parts gives the unit of the degree Celsius. At 0 degrees Celsius, particles still have energy. Absolute zero is a temperature at which particles possess zero thermal energy. 0 Kelvin is defined as absolute zero. The increments between the units of Kelvin and degree Celsius are the same. A temperature rise of 10 degrees Celsius is the same as a temperature rise of 10 Kelvin. A temperature of 273 Kelvin is the same as 0 degrees Celsius. A temperature of 373 Kelvin is the same as 100 degrees Celsius. To convert degrees Celsius to Kelvin, add 273. To convert Kelvin to degrees Celsius, subtract 273. Let's go through an exam question now. A student determined the relative molecular mass mR of an unknown volatile liquid Y in an experiment as shown. The diagram is in a later slide. The student used a hypodermic syringe to inject a sample of liquid Y into a gas syringe in an oven. At the temperature of the oven, liquid Y vaporized. Define the term relative molecular mass, mR, use the experimental results to determine the relative molecular mass of Y. The gas constant R is equal to 8.31 joule per Kelvin per mole. The first mark is for knowing the definition of relative molecular mass. Relative molecular mass is the average mass of a molecule compared to 1/12 of the mass of an atom of carbon-12. This can be written in a sentence or as an equation shown here. There was 1 mark for this definition. Now, let's address the rest of the question. The table of results is shown here alongside a diagram of the apparatus. First of all, we can work out the mass of liquid Y injected into the larger gas syringe. Subtract the mass of the smaller hypodermic syringe after injection from the mass of the hypodermic syringe before injection. 10.91 minus 10.70 works out to be 0.21 grams. Next, we had to convert the units of temperature from degrees Celsius to Kelvin. Add 273 to 98.1 to give a temperature of 371.1 Kelvin. The pressure is given in kilopascals. To convert to pascals, multiply by 1000. The pressure is 102,000 pascals. The volume must be converted to meters cubed. To do this, divide by 1 million. A quick way of doing this is by using times 10 to the minus 6. The volume of gas is equal to 85.0 times 10 to the minus 6 meters cubed. Here are all of the variables given with their appropriate units. There was 1 mark awarded for these conversions. Next, we have to know that the ideal gas equation is PV equals nRT. You will notice that we have values for all of these variables except for amount of substance N. For the third mark, we have to rearrange the ideal gas equation to make N the subject. N is equal to PV over RT. Substituting the known values into this equation gives the value of N to be 2.8114 times 10 to the minus 3 mole. The amount must be quoted to at least 3 significant figures for the fourth mark. I have given this in-process results of 5 significant figures to avoid a rounding error in the final results. You should be familiar with the amount equation of amount of substance N is equal to mass divided by molar mass. We can rearrange this to make molar mass the subject. Mr is equal to G over N. The mass of Y was calculated from the results table earlier. This is 0.21 grams. The amount of Y has just been worked out using the ideal gas equation, 2.8114 times 10 to the minus 3 moles. Substituting these values into the equation, Mr is equal to 74.7 grams per mole. I have given the answer to 3 significant figures consistent with the data in the question. This answer was required to gain the 5th and final mark for this part of the question. Here's the final part of the question. Some of the liquid injected did not evaporate because it dripped into the gas syringe nozzle outside the oven. Explain how this would affect the value of the Mr of Y calculated from the experimental results. You should recall that to calculate molecular mass we divide mass by amount of substance in moles. In this scenario, the actual mass injected is less than 0.21 grams, so the calculated value of Mr will be greater than the real value. 1 mark is given for each of the 2 points shown in blue here. Well, that was the first FlipChem video of 2025. Happy New Year to all new and returning viewers. Just before Christmas the channel reached over 500 subscribers. Thanks for all of your support. I hope you find the videos useful, but please do post in the comments if you have any questions or suggestions. Alternatively, you can send an email to the address shown here. Take care and good luck with your studies.